point, I'm going to open up this console window, which I have already logged into, and I've logged into the MySQL server on the CS server here locally. And those of you who were in my advanced web programming class last semester, I think I did an SQL lab there for you, but then never required you to do SQL. But you might recall that one command I haven't executed here yet is there are a couple of databases that I can access here, and one of them is the university database, whose data was provided by the authors of the book. So I'm going to use that university database, and now I can type in the command show tables. What tables do I have access to? All commands in SQL in MySQL have to terminate in semicolons. And by the way, you might notice that Microsoft Access tries to put semicolons at the end of everything that you type in those SQL views. So if I don't put a semicolon here and hit return, I believe I've talked about this before, it thinks that maybe I'm trying to type in a multi-line statement, and so it's not going to execute anything until I give it that semicolon. And here we're going to see that all of the tables that you have represented on your database schema are uploaded already into the CS server MySQL database. And so, for example, I guess before we've only seen the data in these tables when the author would give us pictures of the output of their select statements. But if we wanted to see all of the data in the student table, for example, select star from student. It builds us a little ASCII table representation of that data. So the student table has 4 columns of data. If you have your DB schema in front of you, it shows you that the student table only has 4 fields: ID, name, department name, and total credits. And it turns out that there's only 13 records in that student table as provided by the author of the textbook for this course. And so apparently these are just last names. Name means last name here, and so we've got student Brown and Snow and Sanchez and Levy and Chavez and Brandt and Shankar and Chang. We also know which departments they're currently majoring in. Apparently that's what department name means in the student table. We've also got the instructor table. So select star from instructor. And you've probably seen Srinivasan and Professor Wu and Professor Mozart and Professor Einstein in one of our recent snapshots of the contents of, or the return values of some query. And so here is all the base data before this table gets joined together with another table. This is what the raw data looks like inside those tables. I believe on your database schema you've also got an advisor table, right? I could probably look. No, that just shows past commands. I could probably scan up here just to make sure I know the correct name. Advisor table. Okay. Let's see what's in the advisor table. There's probably a command that shows the structure of the advisor table. I don't recall it right now. Anyway, I'm probably more interested in seeing the data. Select star from advisor. Advisor table apparently only has 2 columns, 2 fields according to your database schema. The S_ID field and the I_ID field. You might recall that, and the meaning of these combined values is this student is assigned to this instructor. And what does this number 76653 refer to? What does this number 98345 refer to? probably 98345 in the instructor table, and there's probably an instructor ID, a student ID of 76653 in the student table. And so that would mean that that student with that ID is the advisee of this advisor. Professor Kim is advising whoever 76653 is. So this is this advisor table is an example of the foreign key concept. That is, we're taking raw data from some other table, raw data that represents basically an entire row of data. The value 98345 in the instructor table represents Professor Kim, who is in electrical engineering and makes $80,000 a year. But we can basically have access to all that data just by moving this value around. And so that means that this value is foreign to this table, but it's native to that table where it's representing its row. And while I'm still thinking about it, student number 98765, I'll just scan up in my output here to see who we're talking about there. That ends up being student Barikas, who is an electrical engineering student. I guess it makes sense that they have an electrical engineering advisor. And student Barikas has completed 98 credits of courses so far. And this is kind of how data from different tables gets matched together, is finding representative values, keys, unique ID value, unique values from those tables to represent those rows, so that in other tables, when Tanaka is taking a course or something, we'll just represent that student not with the name Tanaka, because there may be multiple Tanakas, but since everybody has an individual star ID, we'll just use Tanaka's ID, and then we know that it's student Tanaka, and if they were a professor Tanaka, we wouldn't confuse the two there. And if Tanaka had a sibling also taking courses at the same time, we wouldn't confuse this Tanaka with their sibling, because their sibling would have a different student ID. All right, now that we've kind of seen what's going on inside this database here, do you guys remember any other I've just shown you some basic select star from select SQL selection queries. Do you remember any other query stuff that we can use to make this fancier? Select and from, we have the where clause, right? Maybe we want to select only those students whose ID is greater than some value, only some instructors who are making more than some base value. That's what the where clause would be used for, typically. Let's see who the highest paid instructors are at this university here. That would be something like select everything from instructor where, and I could put this on multiple lines if I want. Why did it? Okay. Instructor. Where, what must the median price, median salary of an instructor be at this university? Where salary is greater than 50,000, for example. If I hit return now, it's going to wait because I didn't give it a semicolon. I guess that's most of the instructors. Did it filter out any instructors? There's 11 rows in this results set. Well, and there were 12 rows in the original set. Okay, so I only filtered out Mozart, the music professor. Only professor making less than $50,000. But that's what the where clause is used for. We also often use the where clause when we're representing relational algebra statements that had some predicates. That often occurs in the where clause, although some predicates can occur in other clauses as well. All right, since we've seen some of these basics in an actual live running SQL Server environment, let me talk about the join statement, which is not going to be very useful to you in homework 4 due next Friday, but in assignments where you're actually dealing with this win data that you have uploaded into your Access database, you're probably going to want to use joins a lot to filter down to the data that you actually care about and filter out all of the irrelevant data from the rest of that data set. So if we were to use the university database as a model, and we wanted to find instructor names and the course ID of the courses they taught, have I asked you to build a relational algebra statement like this already? What would that relational algebra statement look like? Where from your database schema is this data going to be coming from, according to this prompt that some muzzle user has come to your office and asked you to execute on your database? Instructor names and the course ID of the courses they were teaching, I guess, or that they taught. The English language is a little bit tricky. A statement like this can be interpreted a couple of different ways, but where do you suppose this information is going to come from? Which are the tables in your database schema that you probably want to focus on? Need to get a database schema myself. I'm looking at my database schema. I see a course table. It's got course ID in it. Do I need data from the course table? They were asking for instructor names. I know that instructor names comes from the instructor table. We'll probably need the instructor table in all of this. And the course ID of the courses that they teach or that they have taught. Maybe do I need stuff from the teaches table? Do I need data from all three of those tables that I just mentioned? The teaches table, the instructor table, and the course table? I mean, I would say the answer to that is probably no. Only because the only information I seem to require from the course table is course ID, but I can get course ID from some other table, right? I see that there's a course ID field in the teaches table, which was already another table that I was considering getting data from. And I mean, let's keep this SQL query as simple as possible. Let's use as few tables as possible to get our data from. So I think probably a minimal set of tables would just be teaches and instructor, right? So can someone tell me, what would you rather do first? Would you rather just come up with an SQL statement, or would you rather build a relational algebra statement and then translate that into a SQL statement? I mean, maybe relational algebra is a little bit more symbolic and maybe a little shorter and requires me to think of fewer details. I want instructor names and the course ID of the courses they teach. So I'm thinking I'm probably going to need to select stuff from the teaches table.
Teaches course ID.
Which so from there I'll get at least course ID. I'll also in there have ID, which is actually instructor ID. It's not student ID. I can tell that by where the line goes. And so that's going to be the common data between those two tables. And so I feel like I'm going to grab stuff from the instructor table. I'm going to grab stuff and connect it with stuff from the teaches table. What is the symbol that does that connecting in relational algebra?
Cartesian product.
Cartesian product. What's the symbol for that? Big X? Okay. And then I probably just don't want a bare naked X here. I probably want a predicate on that X. Do you remember what kind of predicates I tend to put on Cartesian product X's? I don't know if that's something that I invented or if I saw in a book somewhere, but that's where I've been putting those predicates ever since. And the reason I don't want a bare naked Cartesian product X there is if I don't give it a predicate, it's just going to match every row in instructor with every row in teaches. And I don't think that's what I want here, right? I don't want a combination of everything with everything. What do I want?
Where the IDs are equal to each other?
Yeah. So let me just represent the table teaches as T and table instructor as I, just so my predicate is a little bit shorter, but basically where I.ID is equal to T.ID. All right? So grab everything from the join of the instructor table with the teaches table, and but only return combined rows where those IDs are the same on the two rows that got joined together. Yeah, I think that's. Oh, and all I want to return from this mess is just instructor name and course ID of the course they taught. I know that instructor name is going to come from the instructor table. I know that course ID is going to come from the teaches table. So, and I don't want to really see the values in the other fields here. And so I guess to finish this off, I want to filter out column names to only be I.name and T.course ID. Does that make sense from a relational algebra standpoint? Of course, this is not something that I can type into Access or into my console window and have CS actually give me a result because I don't know where my pi key or my sigma key are. So I don't have a relational algebra interpreter on the CS server MySQL database. And so if we're going to type this into the database connection that I've established here, we're going to need to translate this into SQL. So we're going to start with some SQL keywords. I'll just capitalize them so that they're obvious. Most every grab data out of the database query that we build will start with the keyword select. It's the most common type of query that we give to databases. What are we selecting? Values from these column names. If we want everything, we would use star, but since we know we only want name and course ID, since a name doesn't appear in teaches, and the course ID doesn't appear in instructor, those are unique values. We don't really need to precede them with the names of the tables that they came from. I'm going to do that anyway, even though it's not necessary. So we want instructor name, so select I.name, comma, T.course ID. I'm going to go to the next line for the next clause, give myself a pattern to copy when I actually type this in to my console window. Where am I selecting these columns of data from? It's expecting table names here. And so the table name is going to be instructor and teaches. And since I've got multiple table names on this line, I have to put something in between, but it turns out that the SQL keyword for Cartesian product just happens to be comma. So if I'm separating table names with commas, then that's just going to do a Cartesian product on all of those tables. And if I'm doing what's called what I call a comma join, I'm going to put this predicate in the where clause. This predicate is already in the select clause, so time for a where. Where, oh, here's something that, since I used shorteners here, I have to do something like rename these values as I and
Teachers is T.
teaches as T
Yeah.
in order for I and T to make sense to the database when I get around to typing that in. Okay, where I.id is equal to T.id. I mean, I really like how relatively easy it is to translate from a relational algebra statement to an SQL statement once you know where all the stuff is supposed to go. Most predicates go in the where clause, the table names go in the from clause, and then the field names go in the select clause. And we haven't really talked about renaming operators, but the author talks about if we were actually explicitly renaming tables in the relational algebra statement, we would use arrows to do that. And so arrow actually translates to the keyword as. And if I'm capitalizing all of my SQL keywords, I should probably let you know that as is a keyword recognized by SQL. All right, I think that's pretty much it. So this SQL query that I've puzzled out here based on this prompt is, this intent is what the author calls it, is hopefully what the author came up with as an SQL query. The author may have come up with something different, but if he did, it'll probably do approximately the same thing. Yeah, it looks like we mostly did the same thing. I just renamed instructor to I and teaches to T, and then I used those prefixes instead of typing out the entire name, and I actually notated where those columns were coming from in the select clause. So I guess this means I have a hopefully valid SQL statement that I can type into my black console window. I'm going to escape out of this guy here, come over here. We've already seen the instructor table. I guess this is the instructor table. Let's look at the teaches. Let's just get a look at the raw teaches table before. Select star from teaches before it gets joined with anything else. So apparently we've got a Bio 101 class and a Bio 301 class, both taught by instructor ID 76766. And, where are the computer science classes? Computer science 101, 190, 315, 319, and 347 are being taught by instructors, binary instructor 10101, and another instructor 83821, another instructor 45565. So apparently all of the computer science classes are being taught by 3 separate instructors. Although some of these classes are being taught in different semesters and years, so they're not all being taught this semester, I suppose. We have 2 sections of CS 190. Anyway, those are, I guess that's a historical list of classes that have been taught on this campus over the years that this data covers. So I suppose classes instructors taught in that original intent was pretty accurate. Now that I've got an SQL query on the whiteboard over here, I'm just going to try to try to type that in. Select I.name T.course ID. This is where I actually have to pay attention to spelling my field names correctly. I usually shorten them when I'm writing stuff on the whiteboard, but not today. From instructor as I, this comma means we're doing a Cartesian product, and teaches as T, and just to show you, just to prove to you that I'm not lying to you when I say that if I don't put this where clause in, if I don't include that predicate, it's basically just going to give me a whole big Cartesian product of the the instructor table and the teaches table. There it is. In fact, I'm only showing you 2 columns out of that joined table, but it's 180 rows tall because every course ID, Bio 101, is being combined with every professor. And so it's basically number of different courses with number of different names long. So yeah, that's probably not what we want. Luckily, MySQL does give me the ability to hit up arrow to show me the last statement I typed in, or access the history of statements that I've typed in, so I can modify if I've made a mistake, where I.id is equal to T.id. This should be less than 180 rows. Oh, just 15. And, let me modify this again, just to make sure that I really have only joined the rows from the instructor table that have the same ID as the rows in the teaches table. Let me just replace this filter here with select star. And so that's just going to give all of the combined columns together, just a massively wide table. But that table will still only have 18 rows if everything is correct. Of course, they're broken over a couple of lines since my window isn't wide enough. See if I can change that at all. Oh man, do I need to rerun it? Let's try that. Okay, that's a little bit more readable. And we can see that the instructor table is the left half of this joined table. The course table is, the teaches table is the right half. That matches the order in which I typed those names in the from clause, you might notice. And I have ID appearing in both of those, and so that's why if I were that's why if I ever do refer to ID in this table, I'm going to have to prepend it with either the table name or the shortened alias that I gave it, I or T, or instructor dot or teaches dot. Because otherwise, SQL doesn't know which ID field I'm trying to refer to. And in this case, I guess it doesn't matter, because if both ID fields do have the same ID, that was the predicate that we gave, the Cartesian product. The join command there in the where clause. But yeah, the reason I wanted to see the whole table was to make sure that these 15 rows that were being returned were all rows where these values matched on every row. So I can see that that predicate is being executed for me. What I asked for. It's only showing me combined rows from that comma join where the instructor ID value is exactly equal to the teacher ID value on the row that it was joined to. Does this make sense? So generally, whenever you make a join, you're going to have to give it some sort of predicate saying where this field value is equal to that field value. Otherwise, you're just going to get a raw Cartesian product that is going to be not very useful to you. And that is the cost of using a relational database where we have all of our different entities split up into different tables. But we are using representative values from some tables in other tables as foreign keys in order to be able to make connections between those tables. That's why there are so many lines between those the tables in your database schema. There's probably no table in your database schema that does not have a line to another table. Those lines mean that those tables are connectable on those fields. Those fields have the same type of data in them. They can be compared. They can be set equal to each other. And that's how tables generally get combined. All right, well, so that's one query off that slide. I bet I had another. We already know the relational algebra for this statement. So let me move on to another statement. I've got the author provided you with a picture of the section table and the course table. So what is this intent saying? We want a table that tells us the course ID, the semester, the year, and the title of each course offered by the computer science department. And the reason that I'm grabbing this data from two tables is if I'm looking at the course table, I don't have any values for semester or year. And so I have to find one of the tables that's connected to the course table in your database schema. And is there a line directly connecting the section table to the course table? Yes, there is. So the author just erased all of the other lines, but pasted those two images in. And so, of course, this line does mean that this foreign key value, course ID in the section table, is exactly the same data type and drawn from all of the values in the course ID field of the course table. And that is sort of obvious just because they have the same name, but sometimes you will have fields in different tables with the same name that don't have the same data at all. And so it's nice having an arrow confirming for us that this is the case. So, find the course ID, semester, year, and title of each course offered by the computer science department. How should we approach this? Do you want to go straight to the SQL, or do we want to prep with some relational algebra? I think I'm more than halfway through the class here. Let's see if we can go directly to the SQL. If we can predict what the author is about to say in the book for this problem.
Would it just be
Yeah.
select course ID,
Yeah.
comma, semester, comma, year?
All right, see if this is any better. But yeah, now we've got some pretty good clues into which clause to put the details that we see in these intents. The select clause is going to be the columns that we care about. And so I am looking for course underscore ID. I might have to prepend a letter at the front of that, but we'll see. Course ID, comma, semester, and that's spelled semester. Year, and title, which is also the field name in the course table. So those are the columns of values that I want out of those two tables. And other than course ID, they don't have any other values in common. So So at most, I am definitely going to have to prepend course ID with either section or course, or whatever I shorten those names to, whatever aliases I give them. But okay, that's select, and I make my aliases on the from clause, so I don't know what letters to put in front of course ID now. What tables am I drawing this data from, Mr. Kapiski?
Section, comma, course.
Yeah, section, and I'm just going to rename that as S, so I have less to type, and comma is going to cause the database to do a whole lot of work, because that's Cartesian product territory there. And then you said section and course, which I'm just going to shorten to C. All right. Where? What do you suppose I need to put in my where clause? Beta? Aiden?
S dot course ID and C dot course ID.
Yeah, that's probably pretty good. Where S dot course ID is equal to C dot course ID. C dot course ID. Maybe? Good. At least it's something that I can type into the database connection and get a result back. It might not be the result that this user was asking for, but it's part of the way there at least.
Yeah, won't that just give every department instead of just the computer?
Yeah, that is very true. I should probably add something else into the where clause. I should also probably correctly type the name of the section table. While I'm thinking about it, what does the selection table look like? Or the section table? Select star from section, just to get an idea of the data. Okay, buildings, room numbers, time slot IDs, course IDs, sections, semesters, years, fine. And of course, probably all I want is these CS courses here. But okay, let's see what this gives us. Select. Okay, do we want the course ID from the section table or the course table? It shouldn't matter because they'll both be the same, so somebody just needs to give me a letter.
S.
S. Select S dot course ID, course underscore ID, comma, semester. Tell me when I mistype stuff. I'm not a good enough typist to actually watch what I'm typing as I'm typing it. I'm always looking somewhere else. From section as S, comma, course as C, I think that's enough. Where S dot course ID is equal to C dot course ID. If I think that will give me my answer, I give it a semicolon and hit return, and then I realize that Mr. Kapiski was right. This is giving me the filtered result of those two joined tables, except it's joined every course with its section information, and what the user wanted was only the CS courses. How do I just filter this down to the CS courses? I suppose some of you might be thinking where the first two letters of course ID are capital CS, but that's going to make me look up how I do a string slice in SQL, and I don't want to do that. And so instead, what I'm going to do is look inside the course table and see if there's any other information that I can use in the predicate to focus in just on computer science courses. So that's the instructor table, keep on going. I don't have a course table, do I? Oh my goodness. Select star from course. Oh hey, there's department name. I can use where department name, again, paying attention to the spelling so that Python understands what I'm talking about, where department underscore name is equal to the string comp period space psi and string, I believe, right? No, there's a dot there. Boom, okay. And since this is a compound Boolean statement here, I need to use logical operators to connect this condition with that condition. And just like in Python in Python, we're going to use the keyword and. I was about to say C++, and then I remembered, oh no, C++ uses ampersand, just to be more confusing to non-computer science majors. But okay, SQL is at least moderately readable for non-computer science majors. I think that'll work, and all I have to do is hit my up arrow a couple of times to go back in history and modify this statement here. In fact, I'm just going to hit return to make it multi-line so it's a little bit more readable. And dept underscore name is equal to the string comp dot psi. And if that string is correctly spelled, typed in, then this should return only those courses and the times, the semesters and years in which they were taught, according to the base data in those two tables. You're not excited by this, Aiden? This result does not fill you with joy? Think of all of the work that the CS server went to just to generate these 8 rows for you. It combined every row in the course table with every row in the section table, and then filtered all of those rows down to these 8 rows that exactly answer that user's question, that intent that user came to your office with. This is how databases change the world. Now, a user can come to your office with an intent, and all you have to do is figure out how to explain to your computer what this user intends for you to ask, come up with some SQL query that instructs the database to correctly bind together the correct tables in such a way that values can be compared between tables and a correct result can be returned. Now we know exactly when CS 101 has been taught in the past, once in fall of 2009, again in spring of 2010. Game design was taught twice, apparently. In spring of 2009, were there 2 sections of game design that semester? Probably. Otherwise, that doubled row would look something like a mistake to me. Let's, where does section come from? That's probably from the section table. I need my schema to make sure that there's a section field. Sec ID is what I'm looking for. Sec underscore ID. So let me just modify semester, year, and I guess sec ID I'll put in front of semester. Sec underscore ID, comma, semester year, hit return. And yes, indeed, game design did have 2 sections that year. So that's not a mistake. CS 319 also had 2 sections in spring of 2010 when image processing was taught. The information we can get out of a database, Tyler, come on! That's got to be more interesting than whatever's going on your phone. Any questions? I don't know how many people in this classroom can write programs in like C++ or Python or something, but now that you have yet another language with which you can speak to computers, and particularly to databases, this is the next most powerful thing you can have your programs do automatically, is if you want to go to the trouble, have your programs put together SQL queries on their own as a single string and submit that string to the database, and then have a variable that gets all of the data that comes back on that database connection. But you can automate the process of executing common SQL queries just by typing in the raw text like this into a string, and then having your program send that string to a database whenever it's needed. Maybe you have users select a task from a menu, for example, and then the appropriate SQL commands run to give them the results that they want from that menu item. It's rare nowadays when you write a program that is more than 100 lines long, that does something, at least moderately important or interesting, that it doesn't use a database to get its job done. It's rare that programs are not connected to databases by default. Databases have just become so central in how interesting, important, significant tasks get done with the programs that you write. So, I think I've just run myself out of time. Thank you very much for your attention. I will see you back here on Monday. Have yourselves a good weekend.